Hello, my dear student. In the last period, we have seen about the uh, effect of dilution. Like what happens if we add water to the two different cells, and how does the conductivity as well as molar conductivity changes. To understand the same phenomena of dilution in detail, now we are going to study it through some chemical equation or some mathematical equation and some of the graphs. So let us start our study. If we keep on diluting, what happens? That means what happens to the lambda m, that is your molar conductivity, lambda m value. How does it change for both strong electrolyte and weak electrolyte? Now, strong electrolytes are the electrolytes that almost dissociate completely, whereas weak electrolytes are the electrolytes that dissociate partially in a very small amount. The answers are explained with the help of the following graph. My dear students, you can see the graph here. In this graph, you have on y-axis your lambda m, which is taken in Siemens centimeter square per mole, whereas on x-axis you have taken this c, square root of c, that is c to the power 1 by 2. You actually study the graph in going this direction. This is the direction in which you study the graph, because you have been doing dilution. As you have been doing dilution, the concentration decreases. So as the concentration decreases, this is the kind of graph that we are going to get. You can see that there are two graphs available. One is for KCl and another is for CS3COOH. This KCl is your strong electrolyte, and your CS3COOH is a weak electrolyte. So this is what it happens. Please have a look at this, that KCl has got a very straight line, and in this straight line you can see the straight line that join with the, or that intersect the x-axis, sorry, that intersect the y-axis, and that point we call it lambda m0. This lambda m0 is known as the molar conductivity at infinite dilution, or it is also known as the limiting molar conductivity. Let us study the behavior of KCl, a strong electrolyte. The graph is plotted on the basis of the equation lambda m0 is equal to lambda m0 minus ac to the power 1 by 2. C to the power 1 by 2 is nothing but your square root of c. Then we compare this equation with y is equal to mx plus c. M represents the slope, that is your minus a. C is your y-axis intercept, which represents the lambda m0, which is also known as the limiting molar conductivity, and your x is square root of c, that is what we have taken on the value of square root c on the x-axis, and lambda m is on the y-axis. So we take a graph of y versus x, and then we can find out the value of lambda m0 as well as minus a. You can see here that your minus a is, if you draw the triangle in this way, PQR. So in this PQR, PQ by QR represents your minus A. So for strong electrolyte, which is linear graph, you get a linear graph of lambda m versus square root of c. Here minus A, or A is the constant whose value can be obtained by the slope of the graph. For KCl, lambda m0 here is called the limiting molar conductivity. That simply means limit C tends to 0, lambda m is equal to lambda m0. This is the mathematical equation. How to write the same mathematical equation into the words? Let us study. When concentration approaches zero, limit C tends to zero. That means when concentration approaches zero, the molar conductivity offered is called the limiting molar conductivity. For the strong electrolyte, limiting molar conductivity can be obtained by the graphical method. You can see that if you extrapolate this graph, or if you arrange the graph to intersect the y-axis, you can easily find out the lambda m0 value according to the equation. How do we get constant A? The value of A for a strong electrolyte can be obtained by using a graphical method. In the graphical method, your slope is equal to minus A is equal to PQ by QR. The value of constant A for a given solvent and temperature depends on the type of electrolyte. That is, charges on the cation and anion produced on the dissociation of electrolyte in the solution. That means here the value of A depends upon the ions which are furnished by a particular salt during the dissociation process, and thus it depends upon the charges that are produced on the ions after dissociation. The electrolyte of same type has the same value of A. So first of all, we should understand what are the various types of electrolytes and how do they furnish ions. So let us study the various types of electrolyte, my dear students. Here you have the various types of electrolytes, like types of electrolyte and example. The first type is 1 to 1 or 1 type. 1 type examples are NaCl, KCl, CSCl, NaI, KBr. Now how do we understand this 1 type? So you can see that NaCl, when gives the ions or dissociate, it gives Na plus 1 and Cl minus 1. As the both the ions have plus 1 and minus 1 charge, it is called 1 type. Now we'll understand about 2 type. 2 type means you have the example CaCl2, MgCl2, BaCl2 and SrNO3 twice. Now what happens here? Your CaCl2 when dissociate, it gives Ca plus 2 and 2Cl minus. So the charge on Ca is plus 2 and charge on Cl is minus 1. So it is called 2 type. 2 type. So you can have MgSO4, CaSO4, BaSO4, MgCO3. Such type of ions, when produced, they furnish the ion. Both positive ion and negative ion have plus 2 and minus 2 charge. So it is called 2 type. 1 type means positive ion will have plus 1 charge and negative ion will have minus 2 charge. So you can see the example Na2SO4, K2SO4, Na2CO3, Na2SO4 when dissociated it gives 2Na plus 1. So here it is the plus 1 charge and SO4 minus 2. Here the charge is minus 2 and that is why the salt is known as 1 type. The value of constant A is same for same type of electrolyte or same type of salt. You can see that for all these various types of uh, electrolytes, the value of A is same. Now let us study the graph for the weak electrolyte, my student, that is CS3COOH. Just have a look at this graph which I am going to explain you. Here you have a graph again for lambda m versus square root of C. You can easily understand. The graph we should study in the direction is this. So when you decreases the concentration, or if you add water or the solvent, this process is known as dilution. So due to dilution, what happens? The graph goes this way, this way, this way, this way, this way. You can see here at this point, instead of graph intersecting this axis, it turns parallel, and we do not know when this graph will intersect your axis. So it is difficult for this graph to intersect the y-axis or lambda m axis. So let us understand the same. For a weak electrolyte, as we are aware, it dissociates partially. When it dissociates partially, what happens? So if we add 1 mole of electrolyte to certain volume of solvent, much of its quantity remains undissociated as it has very less solubility. As we add solvent, that is water, or for aqueous solution it is water, and for other it may be the another solvent, more and more weak electrolyte dissociate. Thus lambda m, that is the molar conductivity, keeps on increasing. It requires very huge volume of water or solvent to dissociate completely 1 mole of weak electrolyte. For solubility, if it is 1 into 10 to the power minus 3 mole per liter, that is, you require 1000 liter of water to dissociate 1 mole of substance. Sometimes the solubility are in the range of 10 to the power minus 6. So this is how you can understand about the weak electrolyte. So as we look at the graph turns almost parallel to y-axis, that is lambda m, and it is not possible to find out lambda m0, which is known as the limiting molar conductivity for a weak electrolyte, by graphical method. So my dear students, we cannot get the lambda m0 or limiting molar conductivity for weak electrolyte with the help of the graphical method. So for lambda m0, that is the limiting molar conductivity for weak electrolyte, is obtained by the Kohlraasch law. So we will study this Kohlraasch law in detail. Thank you, my dear students.